The third set of equations that we will talk is the conservation of energy. Conservation of energy basically consists in the following statement that the energy cannot be created or destroyed. However, it can be transferred. Okay. Um, okay. When we talk about transfer, we are talking about, in the most general sense, you can say that the total energy at location one has to equal to the total energy at location two. However, the relationship of energy, conservation of energy, the delta E, has to equal to zero is not totally correct, because this is actually, it will be zero if we have zero heat transfer and a zero work. Okay, so this is true. So let me erase this. So this will be equal to zero if Q is equal to zero and W is equal to zero. So in the most general case, your delta E is going to equal to Q minus W, where this is nothing else than the heat transfer, and this is nothing else than the work that's happening in the problem. Okay, so this is just a special case for this when you don't have any heat neither work done in the system. And if you remember, this basically comes from the first law of thermodynamics. And the first law of thermodynamics, there are a couple of quantities that it uses. It uses the letter H. H is nothing else than enthalpy, which is nothing else than E plus P times V. This is pressure, and this is volume. Okay, so then this is the internal energy. So in this general sense, that's what you have. So let's go ahead and derive these equations and see how these equations actually look like. And the first law of thermodynamics is saying that my change in energy is going to equal to my change in the work done plus my change in my heat added. So this is the change in energy. This is total work done. This is heat added. Okay, and as you said, both expressions are the same. I have Q minus W here. Here you don't have Q minus W because it's already embedded into these equations. If the heat is added, it's plus. If the heat is taken out of the system, it's minus. So that's why your control volume is so important, because your control volume is going to decide if your heat is taken out, or maybe the control volume is such where the heat is coming in. Okay, so it's all going to depend on how you're working with your heat, and this is going to make it positive or negative, but we go through that couple of examples later on as we move along. So the other thing that we use a lot, and what we really use, is the concept, is the rate change of the energy. And the rate change of the energy, this is the same as the derivative, the this is for a particle, right? This is the derivative of E. And then the total derivative of E. And if you go back to the equation, this is nothing else than delta body plus pressure, work done by the pressure. This is the body forces. This is work done by viscous loads plus your rate change of my heat. So if you want to see how each one of these concepts actually work, this before we move on, this has units of power. Okay, this is the same concept as power. So the rate change of the energy respect to time is what we know as power. So if you're going to do this, let's call this 1, let's call this 2, let's call this 3, 4, 5, and I'm going to tell you what each one of these expressions really mean. So one thing you have to know is that this is so let's go. Let me start in the next page. So this is 1. So let me go to expression number 1. That is dE dt. Okay, so this is the same thing that dt of rho delta v, the volume, E plus velocity squared is equal to this. So now I can, using the chain rule, I take the derivative of this, not chain rule, the product rule, take the derivative of this, multiply by this, and then derivative of this multiplied by this. You can show that the expression that you get is the following. E plus v squared over 2, the derivative of time of rho delta v plus rho delta v, derivative of time E plus v squared over 2. And this expression is actually equal to 0 because by conservation of mass. Okay, because remember, for a particle, the conservation of mass says my delta volume is not going to change, so therefore this whole thing is going to go to 0. Not only that, in respect to time, this is not, the density is not going to be changing. It's the same fluid particle. So this is going to remain the same. It's going to go to 0. And then this is the only part that's actually remaining in my problem. And I can express this whole thing as rho delta v ddt times E plus v squared over 2. Okay? Now, without much derivation, I want to just at least give the expressions for each one of these terms. The body is going to equal to your body force times velocity, rho times delta v. Okay, you can show this is expression that you will get in the problem. Don't forget this is actually equal to ui plus vj plus wk. Okay, and your F is actually force over mass, has units of force over mass. Okay, so that is the work done by the body force. That is equation number 2. The equation number 3, and then we can also go ahead and do a small element, but I'm going to save ourselves all of that and just say the actual pressure is actually equal to the work done by the pressure loads is equal to minus delta V, the change in velocity, change in volume times pressure times velocity. Okay, the gradient or the divergence of pressure times velocity. Okay, so then the next term, the term number 4, Because pressure, the viscous term, pressure number, equation number 4, it says that, and again, I'm going to save ourselves from all the derivations here. I'm just going to give you the final answers on this. The derivations can be found in many of the textbooks, um, but we just care for the final answers, and that's what I really want to focus on. So this will be u times sigma xx plus partial of y, u tau xy plus partial of z, u tau xz, delta volume. Similarly, we can do this in all other axes. So this will be y, this is z, so this will be v. The inside terms change. So this will be tau xy, v sigma yy, v tau xz. This is xz, this is yz, this is w tau xz, this is w tau yz, this is w sigma zz. And most of the times when we are working on with viscous stresses, typically these are zero. All you have is the shear stresses. So that should be something that you keep in mind as you move along these equations. So, and the last term that you have in this equation is the heat. So number 5, q dot, this is the heat transferred by conduction. And it's actually based on this equation where it says partial of t respect to n, where this is the axis in which we are acting on. And you can do a whole full derivation, but I'm going to just give you the final answer here. So the heat conduction, the x direction will be minus k partial of t squared delta volume. Q will be minus k partial of temperature y squared delta volume, delta qz minus k t delta z squared delta volume. T is temperature. Okay, and then I can take all this and I can basically express in a nice big equation which says delta k. You can put a plus sign there if you want to. And let me explain what the plus sign and the negative sign will say. So you can place that plus sign, and then if the conduction is going inside or outside, that's what's going to determine the plus or minus signs, okay? And that would be, so plus minus would come from there. When you say this is the lambda squared, okay, this is not delta squared, okay, so you're basically saying that this is partial of x I plus partial of j plus partial of z k, and you're basically taking the dot product of this twice. Okay, so that's why you end up with this squared, this squared, this squared. So this expression is nothing else than squared plus squared plus squared. Okay, so that's what, I'm sorry, this is this expression right here. This is what this expression really means. So at the end of the day, what you're going to have is a nice expression that you put all the equations back together there. So in the particle system, then we can say this is how equations look like. D rho times d dt of E plus v squared over 2 is equal to the body force dot product of velocity times rho minus the gradient of rho dot v partial of plus partial of x u sigma xx plus v tau xy plus w tau xz plus partial of y u tau xy plus v sigma yy plus w tau x y z plus partial of z w tau xz plus v tau yz plus w sigma zz and plus k times t squared. So this is the particle form of the system of equation. We can write the equivalent form for the fluid system in the integral form, and that's going to look as follows. dt triple integral E plus v squared over 2 rho d volume is equal to the triple integral over the volume f rho d volume plus the double integral over s minus p n plus t of x. Remember, this was your stress vector dot n times I plus ty dot n times j tz dot n times k dot the velocity times s. And then and then the next thing, the last term is your heat transfer term, and it's actually equal to this. So this is the fluid system, the equivalency in the fluid system, and we use this quite often, sometimes even to simplify our problems, depending how you take a control volume. So next you're going to see a couple of examples on how does this really work.